We are replacing the boiler in my new house right now. So where I usually film these videos, there's no heat, so I had to find a temporary location. So that explains this Formica. We should be back to my usual desk in a few days with a brand new 138,000 BTU New Yorker steam boiler. Look at that beauty. It's 138,000 BTUs of water boiling mayhem. Sorry, I was just watching the scene from The Wire where Snoop buys the nail gun.
This is gunpowder activated, 27 caliber, full auto, no kickback, nail throwing mayhem, man. Right here is tight. Well, just nailing up boys, we can kill a couple with this right here. You laughing? I'm in school, dog. Trying to tell you. For real.
So back to the math. Completing the proof that the cardinality of a finite set is uniquely determined by that set requires a significant amount of manipulation of the properties of functions. We've seen these before, of course, like injective and surjective and inverses and so on. But it's one of those things that it's easy to understand at a superficial level without really knowing the ins and outs, and the ins and outs are required here for the proof that we're about to do. So in this video, we're going to really dig into the properties relating to these concepts. This video is going to be full of proofs, so we'll get some good exposure to manipulating these things. When we finish the proof of the cardinality of finite sets, we'll be old hats at this stuff. So here are some of the fundamentals of functions. Okay, so first, composition. We're going to go slowly and rigorously. Most of these proofs I had to do on my own, so follow along carefully, and if you can spot an error, please let me know. We know that given functions f from a to b and g from b to c, we define the composite g circle f of f and g as the function from a to c defined as the equation g of f of a. And note that g of f is only defined when the range of f equals the domain of g. Okay, so injective, surjective, and bijective. We've introduced these concepts before, in particular in our proof of the uniqueness of the real numbers, but just to remind us, for function f from a to b, injective, which is also called one-to-one, means that if f of a equals f prime of a, that implies that a equals a prime. Surjective, which is also called onto, means that if b is in the range b, that implies that b equals f of a for at least one a in the domain. So bijective, of course, means that the function is both injective and surjective. So the composite of two injective functions is also injective, and the composite of two surjective functions is also surjective. So these two claims are easy to check. So take two functions, f from a to b and g from b to c, and two elements, a and a prime, in A. Let b equal f of a and b prime equal f of a prime, and let c equal g of b, and let c prime equal g of b prime. So c equals g of b, which equals g of f of a, and c prime equals g of b prime, and so on. So suppose that f and g are injective. If c equals c prime, that means that g of b equals g of b prime, and that implies that b equals b prime because g is injective. If b equals b prime, that implies that a equals a prime because f is injective. So that's all there is to it. We've proven that if g circle f of a equals g circle f of a prime, that implies that a equals a prime, and that means that g circle f is injective. So suppose f and g are surjective. Then if c is an element of c, then that implies that c equals g of b for at least one b in b. And if b is an element of b, that implies that b equals f of a for at least one a in a. Therefore, just putting those two together, if c is an element of c, that implies that c equals g of b, which equals g of f of a for at least one a in a. And that means that g circle f is surjective. Okay, those were easy. So it follows then that the composite of two bijective functions is bijective because they're injective and surjective. Okay. Okay, so inverses. If f from a to b is bijective, then there exists a function from b to a called the inverse of f. Now, functions only have inverses if they are bijective. And we know this, for instance, from like arcsine, which we've looked at a lot, because a sine goes like this, right? But if you take the inverse of it, it goes like this, and this can't be a function because it's repeating, right? So what we have to do to define arcsine, is cut it off somewhere so that the domain of arcsine is only from minus pi over 2 to pi over 2, and then that keeps it injective and surjective, so bijective, okay? So the inverse is denoted by f minus 1. So the inverse f minus 1 of b is defined as the unique element a of a for which f of a equals b. So given b in B, the fact that f is surjective implies that there exists such an element, f of a equals b. And the fact that f is injective implies that there's only one such element. So it's easy to see then that if f is bijective, then f minus 1 is also bijective. Okay, so now it starts to get more interesting. So let's denote the identity function for a set C by I sub C. So that means that the function IC from C to C is the function given by the rule that I C of x equals x for all x in C. Okay? So given a function f from a to b, we say that a function g from b to a is a left inverse of b if g circle f equals the identity function for the set A. We say that hb of a is a right inverse of f if f circle h equals the identity function for b. So this is really interesting because we're talking about general functions here, but this concept of left inverse and right inverse is seen repeatedly in math. For instance, in abstract algebra, a group G has a left cancellation law, which means that A times B equals A times C implies that B equals C. And it has a right cancellation law, which says that if B times A equals C times A, then B equals C. And then similarly, in linear algebra, matrices can also have a left inverse or a right inverse. So if A, M, and N are matrices of a field F, then if M A equals the identity matrix, then M is the left inverse of A. And if A N equals the identity matrix, then N is the right inverse of A. So there are patterns in math that show up over and over, and this is one of them. So the reason that I'm talking about the left inverse and the right inverse of a function is that there's a useful criterion that uses these inverses, the left and right inverse, to show that a given function is bijective. So, theorem. Let f be a function from a to b. If there are functions g from b to a and h from b to a, such that g of f of a equals a for every a in a, and f of h of b equals b for every b in b, then f is bijective and g equals h equals f to the minus 1. So to prove this, first we'll show that if f has a left inverse, then f is injective. Then we'll show that if f has a right inverse, then f is surjective. Then we'll look at some examples, and then we'll be able to show that if f has a left inverse g and a right inverse h, then f is bijective and g equals h equals the inverse of f. Okay, so first we'll show that if f has a left inverse, then f is injective. So let's assume the opposite, that if g is a left inverse of f, then f is not injective. So injective means that if f of a equals f of a prime, that implies that a equals a prime. So if f is not injective, that implies that there exists an a and an a prime in a, such that f of a does equal f of a prime, but a does not equal a prime. Okay? So let's let G be a left inverse of f. That means that G circle f equals the identity of a, which means that G of f of a equals a. Okay, so choose an a sub 0 and a sub 0 prime of a such that f of a 0 equals f of a 0 prime, but a 0 does not equal a 0 prime. Okay? Now, f of a0 equals b0 for some b0 and b. And since g is the left inverse of f, that means that g of b0 equals a0. Now, we chose a0 prime such that f of a0 prime also equals b0, right? That was how we chose a0 and a0 prime. And since g is a left inverse of f, then it must also be that the g of b0 equals a0 prime. But since a0 does not equal a0 prime, that means that g of b0 has to have two different values. But then g as a function is not well defined, right? It means that it has to have that one value of the domain has two values of the range. So it's not a function. So it can't be a left inverse of f. But we started by assuming that it was a left inverse of f. So we've reached a contradiction. So therefore our assumption is wrong, which means that if f has a left inverse, then it must be that f is injective. Okay, now let's show that if f has a right inverse h, then f is surjective. Now, surjective means that for every b and b, there exists at least one a and a such that f of a equals b, right? That's what surjective means. So if f is not surjective, that means that there exists a b0 in b to which f maps no element of a. In other words, b0 does not equal f of a for any a element in a. Okay, so let h be a right inverse of f. That means that f circle h equals the identity of b. In other words, f of h of b equals b for all b in b. Now, since h is defined over all of b, then every element of b is mapped to some element of a. But f is not surjective. So there's some element, b0, of b, for which there's no a such that f of a equals b0, right? So that means that h maps b0 to some element a0 in a, which does not go back to b0. So this has to be that f of a0 does not equal b0. So that means that f of h of b0 does not equal b0. But this means that h cannot be the right inverse of f because there's some element in b that isn't mapped back to itself. So again, there's a contradiction because we began by assuming that h was the right inverse of f. So that means that our assumption must be wrong, meaning we assumed that f was not injective. That assumption must be wrong, therefore f is injective. It's not injective, surjective. Okay, good. So we're sort of getting our feet wet. We're starting to get into this a little more here. So what's an example of a function that has a left inverse but no right inverse? Remember, the theorem is telling us that if the function has both a left and a right inverse, then those two inverses must be the inverse of f. But is it even possible to have a left inverse but not a right inverse? You might want to pause for a second and see if you can think of one. But how about this? F from R to R with f of x equals e to the x. So that looks like this. So it certainly has a left inverse because anything from the domain that you send up to the range, then it will go back to the same value in the domain, right? But does this have a right inverse? And the answer to that is no, because the inverse function is only defined for values greater than 0. So half of the range is not even defined for the left inverse of this function. So it can't have a right inverse because it's not defined for the whole range. Now, if you defined f so that the range was only the positive reals, then it would have an inverse. But what's the difference? Because in that case, f would be surjective. The problem is that f here is not surjective because f only covers half of the range. So it can have a left inverse, but it can't have a right inverse. Okay, now, is there a function that might have a right inverse but not a left inverse? Yes, what about this? So this function looks something like this. So this is interesting because this will have a right inverse. So what's the issue here? This function doesn't have the problem that f had here because the whole range is covered. F is surjective here. So that means that h is defined for the entire range. Now the issue here is, of course, that this function is not injective, right? So there are multiple values in the domain that give the same value in the range. But if we're starting with the inverse function and then applying f, we can actually handle that okay, because we can just cut out the part that doesn't work. So we can just define h to look something like this. So it's just basically from up to here and then up to here. So in this function, there are parts of the domain of f that are not covered, right? Everything between here and here has no value. The range isn't covered here. That doesn't matter for a right inverse, because all that matters is that all of the domain of h is covered. Even though these values in the domain of f are not covered, that doesn't matter, because what matters is you take something in h, you get some value, and then you're able to go back by applying f to it, right? So the fact that there are extra values here, the fact that f has values from here to here, it doesn't matter, because those values are never going to be reached by this function. So f can do anything you want from here to here. It's not important. What matters is that as you're taking anything in the domain of h, meaning the range of, if this is a and b, when you're taking anything in b, it's all covered, and it returns something that's in a, and then it will return a unique value back to b. But this does not have a left inverse, right? Because the inverse of this, if you flipped it around, it's going to look like this. So if we tried to make this into g, there's no way to cut it out that's going to make it work, because we have to have a value for every value of a. But then the problem is different values of a will return the same value. So that means that then if you try to go back using an inverse function, you're going to end up with multiple values, so this can't even be a function. So what's the difference here? This function is surjective. So that means that it can have a right inverse, but it's not injective, so it cannot have a left inverse. This one is injective, so it can have a left inverse, but it's not surjective, so it cannot have a right inverse. Okay? So if there's a function that's both injective and surjective, then what the theorem is going to tell us is that that function is bijective and that it only has one inverse, which is the left inverse and the right inverse and the inverse of f. Okay. Now, can a function have more than one left inverse? And can it have more than one right inverse? The answers to those questions are yes and yes. For a function with two left inverses, we'll just make one very simple. Okay, so this is a function that has two left inverses. So the left inverse is g of f of x. So the domain of f is 0 and 1. So you go from 0 to 0, and then g1 goes back to 0, 1 goes to 1, g1 goes back to 1, and this g2 is also an inverse. 0 goes to 0, 0 goes back to 0, that's right. 1 goes to 1, and then 1, g2 sends 1 back to 1. So in both cases, the fact that g1 and g2 are different, they're only different for the number 2, but this is irrelevant to f. So the fact that g2 goes to 1 and g1 of 2 goes to 0 isn't important for f's left inverse. So it is possible to have a function that has two left inverses. The way that's possible is that f is not surjective, right? Okay. Okay, so stop again and think, can you think of a function that can have two right inverses? And the answer again is yes. How about this? So this function is surjective because the range is only the positive y-axis, but it's not injective because notice that -1 and 1 are both going to give you the same value. So we can have two right inverses here. So basically what we do is the first inverse is just this half, and then the second inverse is just this half. Both of them cover the range, but we're only looking at half of them. So we're looking for, we have f of h of b equals b, right? Now h1 of b equals plus the square root of b. And then f of h1 of b equals f of plus the square root of b, which equals the square root of b squared, which equals b, right? So it is a right inverse. And if we use the other inverse, we have that f of h2 of b equals f of minus square root of b equals minus the square root of b squared, which again equals b. So this is also the right inverse. So it's also possible to have two right inverses. And the issue here is that this function is surjective, but it's not injective. The fact that it's not injective allows us to create two different right inverses, which still cover the range. So the important thing about a right inverse is that we're not concerned about sending A back to A. We're starting on the range, going back to the domain, and then back to the range. So all that matters is that the range is covered. So here, all of the non-negative reals are covered. So F is surjective, even though it's not injective. Okay. So now we can prove what we want to prove. So now we're going to show that if F has both a left inverse G and a right inverse H, then F is bijective, and G and H both equal the inverse of F. So the bijective part is obvious because we already showed that if F has a left inverse, it has to be injective, and if it has a right inverse, it has to be surjective. So if it has both, then it's injective and surjective, so it's bijective. So that part's kind of for free. Now, since F is bijective, then it does have an inverse. And if it has an inverse, then that means that f of minus 1 of f of a equals a, and f of minus 1 of a equals a. Okay, so we know that it has one inverse, but what we have to show is that this inverse is h and this inverse is g. In other words, is it possible for F to have other left and right inverses? Now, we just showed that it is possible, but is it possible in this situation where it has both? So what we have to prove is that if F is bijective, then its left and right inverses are unique. So assume not. So assume that G1 and G2 are both left inverses of F. So that means that G1 of f of a is a, and G2 of f of a is a for all a, and yet there exists some b0 in b such that G1 of b0 equals a1 and G2 of b0 equals a2, but a1 does not equal a2. And this is possible because there's no element of a that f maps to b0. So there is no f of a equals b0. Okay? So even though G1 maps b0 to something, f doesn't map anything to b0. And this is what we had with the example where f mapped 0 and 1 to 0 and 1, but then g would map 2 to something else, but it didn't matter because f didn't cover that, okay? So this is okay when f is not surjective because then there are extra elements in b that can do whatever they want, just like in the example, because they're not involved in inversing f. But if f is surjective, then for every b in b, there exists an a such that f of a is b. So we assumed that G1 of b0 is a1 and G2 of b0 is a2, and that a1 does not equal a2. So since f is surjective, that means that there exists some a such that f of a equals b sub 0. Now, because G1 is the left inverse of f, this a has to be a1. So it has to be that f of a1 equals b0. Because if it was some other element, so let's say instead that f of a3 equals b0, but then that means that G1 of f of a3 equals a1. And if that's the case, then G1 is not an inverse. So this can't be true, so it has to be that f of a1 equals b0, right? But the exact same argument applies to this one. F of a2 has to equal b0 because otherwise G2 won't be a left inverse of f. But f of a1 has to equal f of a2. Remember that f is injective, so that implies that a1 equals a2. But this contradicts what we started with, because that means that G1 of B0 equals G2 of B0, which implies otherwise, in other words, that G1 equals G2. But we started by saying that G1 and G2 are separate, and we just showed that in fact they're the same. So that's the contradiction. So therefore, if f is bijective, then there can be only one left inverse. And since we already showed that f has one left inverse, it has to be that G equals f minus 1. Okay? So now let's look at H and see if we can prove the same thing for H. So assume that H1 and H2 are both right inverses of f and that H1 does not equal H2. So that means that f of H1 of B equals B and f of H2 of B equals B, but there exists some B0 of B such that H1 of B equals A1 and H2 of B0 equals A2, but A1 does not equal A2. Yet even so, even though this is true, we have to have that f of A1 equals B0 and f of A2 equals B0. Because otherwise this won't be an inverse, right? So H2 of B0 equals f of A2, but then f of A2 has to go back to B0, right? So both of these have to equal B0. And that means, of course, that f of A1 equals f of A2, and we have that f is injective, therefore A1 equals A2. But that means that H1 of B0 equals H2 of B0, which contradicts the assumption that H1 does not equal H2. Therefore, again, if f is bijective, there can be only one right inverse. We already showed that there is one. It's f minus 1. So H has to be f of minus 1. So we've shown then that G equals H equals f minus 1. Okay, good. So this is a good start. We're getting a good handle on how to use the fact that something is injective or is not injective in order to prove something about these functions. This is a good place to stop. Next time we're going to look at the image and the pre-image of a function, which gets more confusing because actually this notation is actually ambiguous depending on what you're talking about. So we'll look at that next time, and then we'll get back to the proof about the cardinality of finite sets. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.